All right, so today we are going to sort of continue on this theme of trigonometric identities, and we're going to introduce some new ones here. And we're going to start off by proving one of them that's going to be the basis for pretty much all of the rest. And today the name of the ones we're looking at are the sum and difference formulas. So the first one we're going to look at is one that relates to cosine. So I'm going to set up a scenario here that I'm going to base this entire proof off of. All right. So let's say that we have an angle opened up in the coordinate plane. This angle we're going to call it alpha. So this first one is angle alpha, right? And then let's say we have another angle that's slightly larger than alpha, and this angle will be angle beta, right? So we have angle alpha and angle beta, right? And then we're just going to go ahead and draw a chord, right, that runs, and this is going to be on the unit circle. I should actually erase this and make sure it's right. So let's go ahead and draw the unit circle first. So here's my unit circle, and then this is going to be a chord of the unit circle, which means it's going to run from this point over to this point right here. So this coordinate is going to be, because it's on the terminal side of alpha, is going to be cosine alpha. Oh boy. It's going to be cosine alpha, sine alpha. Right? And this coordinate right here is going to be cosine beta, sine beta. So those are my two coordinates there. Now, I'm going to go ahead and draw another set of coordinates here in my unit circle. And instead of drawing two separate angles, alpha and beta, I'm going to draw one angle that's going to have the magnitude of alpha minus beta. And incidentally, that's going to be the same as the magnitude of this angle right here, right? This angle is also going to have the magnitude alpha minus beta. So the angle between alpha and beta in my first one is just going to be, beta minus alpha. I'm sorry, beta minus alpha. No, it's beta minus. I'm going to rename these actually. So screw this up right now. Just going to rename my angles here. I'm going to make the smaller one be beta, and the larger one is going to be alpha. So apologies for that. Why this isn't going to work. All right, it's getting a little bit. Okay, let's try this again. All right, so we have up here instead, because I renamed the angles, this one's going to be cosine beta, sine beta. And this one's going to be cosine alpha, sine alpha. All right, so we fixed that. And so the angle in between the two angles up here, this angle right here has a magnitude of alpha minus beta. So if I subtract beta from alpha, I have an angle that has this magnitude, right, which we're just going to call alpha minus beta. Then we're going to go ahead and we're going to actually construct an angle that has that magnitude in my unit circle right here, right? And then the point on this point, on the terminal side of this angle on the unit circle, is going to be cosine alpha minus beta sine alpha minus beta. Okay, and we're also going to have a chord that runs between the 2 points. Having a bad morning with the pad here. So we also have a chord up there. So what's going to be true is the chord that runs between these 2 points should be the same length as the chord that runs through these 2 points, because, right, these are both unit circles, theoretically, and these chords of the circle have the same central angle, alpha minus beta, in both cases. So this chord and this chord should be equal in length, which makes sense, right? And so we're going to go ahead and we're just going to give these points names so I can refer to them by name. So this first point right here is going to be point A. This point right here is going to be P1, and this point will be P2. This point here will be A. Actually, we don't need to name this one. This one over here will be A, and this one we're going to call P3. So we can make a very simple statement that the distance, right, from P1 to P2 has to be the same as the distance from P3 to A, right? Because those chords have to have the same length, so the distance between those points is going to be the same, right? Because the chords are congruent. So far, so good? It's a lot of setup, but once you get there, it just becomes a bunch of algebra. So the geometry is the setup, and now the algebra commences. So, distance formula, do we remember that? How do I set up my distance formula for P1 to P2? I know my coordinates, right? These are my coordinates, and we're finding the distance between these 2 points.
Square root.
It's going to involve a square root, yep.
Cosine alpha.
Cosine alpha, yep.
Minus cosine beta.
Minus cosine beta.
Squared.
Squared, yep.
Plus.
Plus.
Sine alpha minus sine beta.
Yep. Maybe at some point this morning I'll be able to actually write professionally this thing. All right, so there we go. And that's going to equal something that also is a square root, right? What is point A, by the way? What point is that if it's on the unit circle? The point 1, 0, yeah. So we're going to end up having over here, what? This is the distance from P3 to A. So P3 is this point, right? I'm going to need to erase that probably. So what are we thinking? Maybe cosine alpha minus beta minus 1, right, squared, plus sine alpha minus beta minus 0, which is just sine alpha minus beta squared, right? So barely got it in there. So once again, sine alpha minus beta minus 0 squared, but we're subtracting 0, right, the y coordinate, which is just nothing. So we just have sine squared there. So this is the basic setup, right? So we know this is true. So this essentially, this by itself is an identity. It's just not a very useful identity because it's so complex and difficult to work with. So what we're going to do is we're going to go ahead and we're going to try and simplify it down as much as possible. What's the first thing you think we could do that would make this a much simpler expression?
Square both sides.
Yeah, if we go ahead and square both sides, let's go ahead and do that. So if I square cosine alpha minus cosine beta squared plus sine alpha minus sine beta squared, which is going to be equal to cosine of alpha minus beta minus 1 squared plus sine squared alpha minus beta. So, get rid of the square root, and now the next thing we're going to do is we're going to fully expand both sides of this equation. We're going to go ahead and FOIL out the cosine alpha minus cosine beta squared and the sine alpha minus sine beta squared, which is going to be a pain in the butt, but it's going to make things easier. So on the left side here, if I square out cosine alpha minus cosine beta, I'm going to get cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. Right, and then I'm also going to get, and I'm just going to put this all on the same line here, plus sine squared alpha minus 2, whoops, that's sine, not cosine, minus 2 sine alpha sine beta plus sine squared beta. Right. And on the other side here, I only have one thing I have to square out because the sine squared is already expanded. And I'll get cosine squared alpha minus beta minus 2 cosine alpha minus beta plus 1, right? That's what I get if I square out this, right? First term squared, middle term, 1 squared is negative 1. And then still just plus sine squared alpha minus beta, right? So that's where we're at right there. And so the next question is, can we go ahead and simplify this maybe using some of the theorems that I know? What's cosine squared plus sine squared? Yeah, because now we have cosine squared plus sine squared for the alpha here. And we also have cosine squared plus sine squared for the beta here. So those are both going to become 1, right? So we'll end up getting 1, right, minus 2 cosine alpha cosine beta plus 1 minus 2 sine alpha sine beta. So if we apply the Pythagorean identity, we can do that, and we can do that also over here, right? These will also equal 1, so this plus this will give me, and then I'll have 1 plus 1 minus 2 cosine alpha minus beta, right? And so let's just go ahead and combine like terms. I'll end up getting 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta, whoops, don't need that, equals 2 minus 2 cosine alpha minus beta. Right, so we have 2 on either side, so you can imagine we're just going to go ahead and subtract off those 2's. And we're going to then divide the entire, if we subtract off the 2's, right, and then divide the entire thing by negative 2, because negative 2 is a coefficient here, here, and here, what are we going to end up with? We'll get cosine alpha, cosine beta, sine alpha, sine beta is equal to cosine alpha minus beta. I'm going to rewrite that as just changing the side of the expression. And this is the difference formula that I was speaking of earlier. right, so there is your difference formula for cosine. Cosine of alpha minus beta, right, equals that whole rigmarole right there. This is the difference formula. Now, the good news is this is the only, we're going to be doing some other trigonometric identity proofs here in a second. So these, that last trig identity, the difference identity for cosine, has a lot of practical applications, but we can also use it to prove other identities. So for instance, we know what cosine alpha minus beta equals, but what about cosine alpha plus beta? How could we figure that out? Well, we can use the identity we just proved to, and really quickly figure this out, because this is just the same as cosine of alpha minus negative beta, right? Sort of just a really clever way to write the same thing, but negative is the same as positive, right? And so now we're going to go ahead and plug this into our new identity that we have. So that's going to say, well, cosine alpha minus beta was cosine alpha cosine beta plus sine alpha sine beta, right? But now we just have negative beta in the place of beta in every case. So it's going to be cosine alpha, cosine negative beta plus sine alpha sine of negative beta. Now, let's go ahead and apply another identity. What does cosine negative beta and sine negative beta equal to? Come on, guys, you know this one. Cosine of the opposite of alpha of beta. What type of function is cosine? Yes, it's an even function. So cosine negative beta equals what? Also is the same as cosine beta, yeah, because cosine is an even function. Cosine negative beta equals cosine beta. Sine, on the other hand, is an odd function. So sine negative beta is going to be negative sine beta, and so this whole term is going to become negative. So now we have the addition formula for cosine. We have that cosine alpha plus beta is equal to cosine alpha times cosine beta minus sine alpha times sine beta. So we can use that in the following way. So let's say, for example, I asked you to find cosine of 75 degrees, right, exactly. So not using your calculator, but find an exact quantity for that. Right, how could we use this identity that we have just proven to find that value of cosine of 75 degrees? Yeah, we can write it as what? Cosine of what? What are special angles? Yeah, so we know 30, and what's one that if I add to 30 I get 75? 45. 30 and 45. So if I can make this a sum, or a difference for that matter, right, of special angles, then I can go ahead and use my identity. So this is just the same as cosine 30 cosine 45 plus sine 30 sine 45. Fix that. Right? And we know all those values. So we'll end up getting, what's cosine of 30? 30 degrees is the smaller angle, meaning the bottom side of the triangle in the unit circle is going to be bigger. So what's cosine 30? 1 over 2?
Yes.
That's the smaller one, yeah. Sorry, it's going to be larger. X is going to be larger, I apologize. Yeah, it's square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Sine 30, of course, then has to be 1/2 if cosine 30 is square root of 3 over 2. And then sine 45 is square root of 2 over 2. And so we end up with square root of 3 over 2 times square root of 2 over 2 is going to be square root of 6 over 4 plus square root of 2 over 4. All right. So I'll just, question?
Shouldn't we be subtracting?
Oh, sorry, yes, should be subtraction. Mistake. And so we'll get square root of 6 minus square root of 2 over 4 when it's all said and done. So that's an exact value for cosine of 75. That's one of the applications. I can find angles now that are not special angles by expressing them as the sum or the difference of a special angle if it's cosine. So far we don't have one for sine, right? Okay, so the next one I want you to do for me, show me what, right? I want you to establish the following identity using one of the identities we just proved. I want you to establish the identity that cosine of pi over 2 minus alpha, right, well, let's just call it theta. Pi over 2 minus theta is equal to sine theta. This is what we call the complementary angle identity, right? Think of it in a right triangle. 90, cosine of 90 minus the angle is always equal to whatever sine is, right? It's equal to sine of the complement, or cosine of the complement is equal to sine, whichever way you want to think of it. So go ahead and establish that identity using what we have so far. And once again, the hint is to start with the more complicated side, work only one side of the equation, leave the other one exactly the same, and try and make one side of the equation into the other side using the identities that you have. All right, so looking at this one right here, we want to figure out cosine pi over 2 minus theta, is that equal to sine? Let's prove it using our identities. So if we're trying to, probably the side we're going to work from is the left side, 'cause it's more complicated, there's more things going on. And so we're just going to plug this directly into the cosine difference identity, right? So we'll get cosine of pi over 2 cosine theta plus sine pi over 2 sine theta, right? Cosine pi over 2 is equal to what? Is it 1 or is it cosine pi over 2, cosine's the x-coordinate on the point, it's going to be 0, right? So this entire term is going to become 0. Sine pi over 2 is just 1, right? And so 1 times sine theta is just sine theta. And so we've just gotten sine theta. So that's very quickly confirmed that that is true. So now I've shown that cosine of alpha of pi over 2 minus theta is equal to sine theta. Right. So will that help us with the next? I want to show that if I want to find an identity for sine of alpha plus beta. All right, so what is the sum identity for sine? Right, my hint is that we're going to go ahead and we are going to use, right, the identity that we just established, which is the one that says cosine of pi over 2 minus theta is equal to sine. So use that along with maybe our cosine difference identity to establish or to show what sine alpha plus beta is equal to, in simplest form, of course. All right, let's go ahead and take a look at this one. So we start off with sine of alpha plus beta, right? And the first thing we can do is realize that, well, this is just the same as sine, this is just the same as cosine, using that identity I was just talking about, of pi over 2 minus alpha plus beta, right? All right, so what we're going to do is before we actually apply that identity, we're going to apply an identity in a second here, but we're going to rearrange this into cosine of pi over 2 minus alpha, right, minus beta here. Instead of doing it the other way around. And so then we'll go ahead and apply the cosine difference identity. We'll end up getting cosine of pi over 2 minus alpha cosine beta plus sine pi over 2 minus alpha sine beta, right? And then cosine pi over 2 minus alpha is just going to be sine of alpha, right? By that same identity we just used a second ago, by the complementary identity. And in addition, we'll get that sine pi over 2 minus alpha is just going to be cosine alpha, and this will be times sine beta, right? So, there we go. We have sine alpha cosine beta plus cosine alpha sine beta, and that's what sine of alpha plus beta is going to be equal to. And then by a similar process, we can show that sine of alpha minus beta, so we're not going to actually go through the proof of this, but I'm just going to tell you that sine of alpha minus beta is going to be equal to sine alpha cosine beta minus cosine alpha sine beta. So just like with the difference between, the sum difference identity for cosine, with the sum and difference identity for sine, the difference is just the sign in the middle. It's either positive or negative, but the actual order of the cosines and the sines is the same. So now we have the difference identity for sine. So why don't you go ahead, and so these are the two that we're concerned with. So we've established both of these identities now. So why don't you find for me sine of 7 pi over 12 exactly using those identities that you just established and what you know about the sine of the special angles. All right, let's go ahead and take a shot at this one. So sine of 7 pi over 12, I'm going to use the sum identity here, is equal to sine of 4 pi over 12 plus 3 pi over 12. So if I break it up that way, we end up just getting sine of pi over 3 pi over 4, right? Pi over 3 plus pi over 4, which gives me sine pi over 3 times cosine of pi over 4. Whoops. Cosine pi over 4 plus sine of pi over 4 cosine pi over 3. Right, and so we can go ahead and apply all. Now we know sine pi over 3, that's sine of 60, right? Cosine of pi over 4 is 45. Sine of pi over 3, from what we know about our special angles, sine of 60 is going to be square root of 3 over 2. Cosine of pi over 4 is square root of 2 over 2. Sine of pi over 4 is also square root of 2 over 2. Cosine of pi over 3 is going to be 1/2. And so we will end up with square root of 6 plus square root of 2 over 4 is the exact value for that one right there. All right, continuing on, let's look at a couple more examples here. What if I ask you to find the exact value of sine 80 cosine 80, cosine 20, minus cosine 80 sine 20. What would be the exact value of sine 80 cosine 20 minus cosine 80 sine 20? Okay, so we can look at this and we sort of see that looks very similar to one of my sum and difference identities. Specifically, it looks just like the sine difference identity. So by that identity, this is the same as sine of 80 minus 20, which is just sine of 60, which we know to be square root of 3 over 2. So that's pretty quick and easy if we just remember the identity. All right, so let's look at one that's going to involve the unit circle. Let's say if sine alpha is equal to 4/5, and alpha is somewhere between pi over 2 and pi, and sine beta is equal to negative 2 square root of 5 over 5, and beta is somewhere between pi and 3 pi over 2. I want you to find, go ahead and find for me sine, or let's do cosine. Cosine of alpha plus beta. So to do this one, you're going to want to set up your reference triangle just like we have with ones like this in the past. And then once you've set up your reference triangles and figured out everything else you need to know about, you could figure out any of the other trig functions once you have your reference triangles and you have all three sides, which you might need to use Pythagorean theorem for, right? Then go ahead and see if you can use one of the identities to figure out what cosine of alpha plus beta is equal to. And I made a mistake here. For the second range, instead of being alpha, this should be beta. Beta here. All right, so give that a shot. All right, so we need to be able to figure out what we're going to do is, first of all, just to motivate why we're going to be doing the next part, cosine alpha plus beta is going to be cosine alpha, cosine beta minus sine alpha sine beta. So we have sine alpha and sine beta already, but we need cosine alpha and cosine beta to be able to finish figuring out what cosine alpha plus beta is equal to. So we're going to want to go ahead and set up some unit circle situations here for these. So if sine of alpha is equal to 4/5 and alpha is somewhere in the second quadrant, right, between pi over 2 and pi, so alpha is somewhere over here, right? And sine alpha is equal to 4/5, right? So 4, and it's equal to 4 over 5. We'll assume this is not in a unit circle. So it's going to be opposite over hypotenuse in this case, right? And then we can, so it's going to be a circle of radius 5. And then we can figure out what x is equal to using Pythagorean theorem. X squared plus 4 squared equals 5 squared. And so we'll get that x squared is going to be equal to 25 minus 16, which is 9, so x equals 3. So if x is 3, then cosine alpha is then going to be 3/5. Right, so we have cosine alpha. Now all we need is cosine beta. So for beta, I will do the same thing. We were told that beta is in the third quadrant between pi and 3 pi over 2, so beta is somewhere down there. Right? And so we're told that sine beta is equal to negative 2 square root of 5 over 5. So once again, we'll assume that the radius is 5 of the circle, right? And that And by circle, of course, I mean that assuming there's a circle of some radius here. Here, there's going to be a circle of some radius as well. Well, radius 5, right? And so, if I make my reference triangle here in the third quadrant, negative 2 square root of 5 will be the y coordinate, negative 2 square root of 5 with the y coordinate, and the x coordinate will be, sorry, the radius is 5, of course. And so we need to figure out x, so 2 square root of 5 squared plus x squared equals 5 squared in this case, so x squared is going to be equal to 25 minus, well, 2 square root of 5 squared, right, is going to be equal to 4 times 5, which is 20. So 25 minus 20 is 5. And so x is going to be equal to the square root of 5. And therefore, cosine beta will be equal to square root of 5 over 5. Right? And it will be negative because we are in the third quadrant. So negative square root of 5 over 5 for cosine beta. Okay? So we have cosine beta and we have cosine alpha. So now we can go ahead and figure out cosine of alpha plus beta. So I will have to go and do that in the next page here. One minor error here. Because we're in the second quadrant for alpha, cosine should actually be negative 3/5, not just positive 3/5, but negative 3/5. So we originally had sine alpha is 4/5. We determined that cosine alpha was equal to 3/5. Sine beta was equal to negative 2 over square root of 5, and cosine beta was negative square root of 5 over 5, right? So that means that cosine of alpha plus beta is going to end up equaling cosine alpha sine beta minus cosine beta. I'm sorry, that's not what it is. Sorry, it's cosine alpha cosine beta minus sine alpha sine beta. Or did I ask for cosine, right? Yeah, cosine alpha plus beta. And so cosine alpha is 3/5. Cosine beta is negative square root of 5 over 5 minus sine alpha, which is 4/5, times sine beta, which is negative 2 over, it is negative 2 over square root. Well, it's also negative 2 square root of 5 over 5, sorry. So I wrote negative 2 over square root of 5, but if you rationalize the denominator, you get negative 2 square root of 5 over 5. And let's just go ahead and simplify that. We'll end up getting negative 3 square root of 5 over 25 plus 8 square root of 5 over 25. And so if I simplify that into a single term, I'll get 5 square root of 5 over 25, which is just square root of 5 over 5. Right? Yep. So that is one minor error that I just picked up on here is that because alpha is in the second quadrant, cosine should actually be negative in the second quadrant alpha. So cosine alpha should be negative 3/5, and that's going to make this positive 3 square root of 5, which is going to make this all add up to, instead of 5 square root of 25, it's going to make it up to 11 square root of 25. So it doesn't come out quite as nicely as that. So 11 square root of 5 over 25 should be the solution for that one. Okay. Identities to verify some other identities as we have in the past. We should get some practice with that. So go ahead and verify or establish the identity for me that cosine of alpha minus beta over sine alpha sine beta is equal to cotangent alpha cotangent beta plus 1. All right, so try and pick the easier side. Probably pick the one that you know identities for, and go ahead and see if you can get it to equal the other side. Remember, only work one side of the identity, and then show that it's equal to the other side ultimately. What side do you think we should start with?
Left.
We're going to go ahead and start the left side of the equation, so we'll get cosine alpha cosine beta, cosine alpha cosine beta plus sine alpha sine beta all over sine alpha sine beta. Okay, and so let's break this apart into two separate fractions now. Cosine alpha cosine beta over sine alpha sine beta plus sine alpha sine beta over sine alpha sine beta. Quickly, we realize that becomes 1. And here we have cosine alpha over sine alpha, which is going to be cotangent alpha. And then cosine beta over sine beta, which is going to be cotangent beta. And we've verified the identity at that point because we have the same thing that we started with. Okay? Now, another one, let's just keep one of the fundamental identities that we want to know. And that is, I want you to verify that tan of alpha plus beta is equal to tan alpha plus tan beta over 1 minus tan alpha tan beta. So this is the sum identity for tangent, which can be verified using the identities you already know. My hint is to write it in terms of sine and cosine before you try and do anything else. Oh, also, counterintuitively, you probably also want to work what looks to be the simpler side of the equation, the left side. Probably want to start with that side, and you probably want to write it in terms of sine and cosine. So that's my major hint there. So think about that as you try and work through this. Let's go ahead here and get started on this. So tan alpha plus beta, we're going to write that as sine alpha plus beta over cosine of alpha plus beta, right? And that is going to be, of course, expanded out to sine alpha, sine beta, sine alpha cosine beta plus sine beta cosine alpha all over cosine alpha cosine beta minus sine alpha sine beta. Right? Okay, so the next question becomes, what can we do to go ahead and try and get this looking more like this right here? So we're going to use a trick, which is to multiply the top and the bottom by 1 over cosine alpha cosine beta. Right? So that we will get sine alpha, right? And then if we go ahead and we do that, we get sine alpha over cosine alpha and cosine beta over cosine beta. So the cosine betas here will cancel, right? And we multiply this through, and we'll be left with sine alpha over cosine alpha, right? And then over here, the cosine alphas will cancel, and we're left with sine beta over cosine beta. Now, bottom here, cosine alpha cosine beta will cancel entirely, of course, so we'll get 1. And then we'll end up with sine alpha sine beta over cosine alpha cosine beta. And if we just go ahead and write this all in terms of tan, we get tan alpha plus tan beta over 1 minus tan alpha tan beta. So there we go. That has verified the identity right there. Okay? So some of what we're doing in this chapter is verifying identities and showing that they actually work. And other times we're going to be using those identities for more practical applications. So it's important to know these because they come up a lot, particularly later on in calculus. So we have to sort of have these established and down. All right, so your homework for tonight. So that's your homework. I will, as usual, email out the worksheet that comes from, and that'll be it. And I will have the Chapter 6 test solutions in the next day or two. Okay, have a great day.